Hi there. This video will see how rectangular beams are designed, and we'll show that by an example. So we have here a rectangular wood beam that we know the depth for it, and typically this is what in practice is the case. We have the clear floor height, and we know the ceiling height available to us from architectural requirements. So we would like always to use as much as we can of the depth of that ceiling space. So usually depth is kind of you seek the largest possible depth, because this is what makes the beam stronger and resisting moments efficiently. And the question is now, how big is the width here that we need? So B here is unknown, and we have here this beam is simply supported, and it has a distributed load of 200 pound per linear foot, PLF. As a wood, as material, we have different capacities for resisting tension and compression. So wood is stronger in tension compared to compression. So it's prone to being crushed under compression stresses versus just being tension. So the first step here is we need to find the maximum moment. So if we do the equilibrium and shear moment diagram, you will end up with this typical moment diagram of a simply supported beam under a distributed load. So by practice, people memorize that, yeah, simply supported distributed load, maximum stress happens at the middle of the beam, and it's equal to WL squared over 8. If you don't know that, then you will have to do the detailed statics and shear and moment diagrams. But we're not focused more onto that. We're focused on how to deal with stresses and size rectangular beams for that. So let's say you did the statics and strength, shear and moment diagrams, and try it maybe yourself, and you'll find that it's equal to WL squared over 8. And W here is 200 pound per linear foot, and the length here is 12 feet over 8. That will give us 3,600 pound-feet moment. Next step is to identify the controlling failure here. So which one will be the first failure to happen? Failure under compression or failure under tension? And we're thinking this way because the beam is symmetrical, and I have only one type of moments happening, which is a positive moment here. So it boils down to really which stress limit will be reached first, because it's a symmetrical section. So always sigma top and sigma bottom are equal. So they will increase equally until one of them will hit the lowest limit I have. And in our case here, the lowest limit for stresses is the one on the compressive side. So sigma allow negative. So this is the limit that I will design based on. And now once I know the limit, I know the maximum moment, we need to find the required value for B. So always our criteria or constraint for stresses is that sigma max should be always less than or equal to sigma allow. And my sigma max here is equal to maximum moment times C over I. And this is now my limit is the negative capacity or negative stress allowable limit here, which is 7.2 KSI. So if I plug in everything here, everything is given except for when I calculate the moment of inertia, I'm missing the B value. So this is what I'm really after here. And by solving that, I will find that B should be more than or equal to almost 2 inches, 1.2 or 1.19 inches. And if you see in the problem description, the wood sizes are in half inch. So we need to round to the closest half inch. And that means we'll use 1.5 and 5.5 wood beam for this load that's shown to us and the span of the beam. So it's that simple because the problem is really simple. It is a simply supported beam, so they have only positive moment here happening. There is no length of the beam is subject to a negative moment, And even if this is the case, we have a symmetrical section. It's a rectangular section. So always the positive and negative stresses within the section are equal. Top and bottom stresses are the same because the centroid is in the middle of the height. So it's simple example. Typically, we design the beams to figure out the depths because to figure out the widths because the depths are kind of our goal is to maximize the depth of a beam always, and considering the space availability within a building or within a machine. So you always try to maximize the depth that resists the moment, the bending moment here. All right. We'll see you in future videos. Take care.